recording. Right. So now, just to finish off the sort of discussion on first we looked at the types of signals and the effect that they have on the system. We looked at the impulse and we looked at the step, and then we looked at what happens if you have discontinuous signals and piecewise continuous signals passing through. And now we're going to talk a little bit about the characteristics of the signal of the systems, which is the first part was more on the signal side of things. Now we're talking a bit about this system and some terms that will appear here and in other parts of your program from time to time. These kind of characteristics, or the terms that you're going to hear, are causality, memory, time invariance, linearity, and bounded input, bounded output. Those are how we characterize the types of systems that we will normally deal with. Now, the thing is, and we mentioned this before, we said that there are systems, most times what we want is to have a system whose response is only as a result of something that we do. So you turn it on and then it behaves in a particular way. What you don't want is a system that is trying to predict what is going to happen. All right? Now, a system is causal if the output does not anticipate future values of the input. Right? So the system is not trying to predict things. And in other words, it depends on only of the values of the inputs up until that time. So that particular system that we looked at, after we solved it, the simple RC circuit, is causal since you're not going to get a voltage coming out before you put a step voltage going in or an impulse going in. Okay, which is good for us, because if it had something going on, then we would be in an issue there. So you look at the system and you try to figure out if, given a description of it, you try to figure out if the system is causal or not. So look at that example here. Y is x squared t minus 1 ut. Now ut is another way to say, remember we said that if you multiply something by the unit step, right, unit step does that. So once you multiply something by a unit step, what you're basically saying is everything before the unit step, before t equal to 0, is 0. And everything at t equal to 0 and greater than t equal to 0 is going to be whatever the system response is. So if I look at that example right there, yt is, first of all, by putting the unit step, we're saying that the system is causal anyway, because it's can't stop before t equal to 0. But even more formally, if you look at it, output at time 5, for instance, depends on the input at time 4. In other words, it's not looking at a future value. Y5 depends on something that has happened, so it's not predicting or anticipating. If you look at the other example though, yt is xt plus 1 ut. So y5 depends on an input of a future value. I am in time 5, but I'm depending on a future value at time 6. Notice that the unit step here seems to indicate that at least it's starting at t equal to 0, right? But it doesn't necessarily mean that it's causal, all right? So this one, you have to look specifically at what the sort of time description is doing in a broad sense. So y5 is depending on input in the future, right? It doesn't happen in our world. It happens in science fiction. Then you look at this other one down below. This is a discrete time system. How you know, again, as we said in nomenclature, the fact that you see something in what is looking like array brackets or square brackets means that these are numbers or values. So here's a discrete time system, and y at instant 5 depends on x, a past input. So it appears causal. But then if you look at it, if you're not told anything more, why these numbers n can assume negative values as well. So if n was -5, then what you have is that y at time gone past is depending on x5, which is a future value. So unless you specifically say that n has to be a positive number, then that system on top there is not causal. All right? And causal means another way of you'll meet it as predictive systems, and those are very, very difficult to deal with. And the word is causality. The word is causality, not casualty. Casualty is a hospital, a department in a hospital. This is causality. So all good for us that all real-time physical systems are causal because time moves only forward. So good thing for us is that what is going to happen now to us is really as a result of things are input now or an input in the past, not something that is about to happen. So again, if you imagine if you are a businessman and you had some knowledge of tomorrow's stock price, right, today, just think of what you could do, the money you could make or the damage you could do. All right. Now, causality is a time function. All right. It's something to do with time and how time moves. It doesn't apply to spatially varying signals. In other words, signals that vary over space. For instance, gravitational fields, right? Electromagnetic fields that vary. They may vary with time, but they also vary with distance and dimension. Audio signals are something of that nature as well. So you listen to a sound, the sound itself is varying with time, but how it propagates or spreads over distance is a spatial variation, right? Causality doesn't apply to that part. It will just apply to the time varying part. And it doesn't apply to recorded systems. So a lot of computerized systems have information stored, recorded information. Because it's recorded, you could go into the information at any point in time. So in other words, you could go into the future of a particular value. So recorded signals are by their nature not causal because you could move back and forward in time. Yes, Mario?
Oh, that was a mistake. Sorry.
Oh, hands up or down again, right? Yeah, so recorded videos, recorded information, sorry, cannot be causal because you can move into the data at any point and you can move forward in time or backward in time. The other characteristic of systems is system memory. Now, memory implies storage. The system has to remember in whatever form something about its state. So a system is memoryless if at any time the value of the output depends only on the value of the input at time t. It doesn't depend on something that has happened before. So resistive systems or something, a network of resistors for argument's sake, is memoryless. The current or voltage across a particular resistor or through a particular resistor at a time only depends on the value of the input at that point in time. It doesn't matter what happened any time in the past. However, something like this, where we have a capacitor, the capacitor can store a value. So unless we specifically say that the capacitor is discharged, when we start doing some sort of analysis, the system is assumed, sorry, an RC circuit is has memory, so it is not memoryless. It stores values, and the voltage on the capacitor depends on the past events. What was it being charged? What was it being discharged, and so on. And notice capacitor, the voltage on the capacitor depends on an integral. So an integral is a summation. Remember, an integral is shorthand for a summation over time. So it depends on past values. Okay. So for that thing, a memoryless system has no energy storage components, and it's not going to do any derivatives, integrals, or has any delays in whatever equation describes its operation. So from the time you have a derivative or integral or a delay somewhere in there, it means that you have to store values. And if you're storing values to be used, then you can't be memoryless. All right? A memory system may have one or more storage component, and of course it will do it will do things like integrals and delays and the like. We will meet both. As we said, a resistive system is memoryless. A lot of the electronics that you meet, especially microprocessor electronics type systems, are memory. They work on memory. They store values. So those, by their very nature, have memory, but they can be causal. Right? Remember, the two are not necessarily disconnected. Right? And forget this table. This table was an attempt to summarize something, but I am not too happy with it. So just exit out here. Forget the table. But this part here, right? You can have causal memoryless systems. So for instance, as we said, a resistive network, okay? What it doesn't have any storage element in it. Inductors are storage elements, capacitors are storage elements. So a resistive network or a system that behaves as pure resistance can be causal. It only reacts when you turn it on, and memoryless. We can have causal and we can have memory. The vast majority of systems that have capacitors or microprocessors in them are memory type systems, and they can be causal in that we could turn them on and we put an input, and it's only after the input that we get a reaction. Or they can be non-causal. For instance, if it has storage inside of it somewhere and you're replaying the storage, then you're not dealing with a causal system there. So you could have both causal and non-causal memory systems. And then, of course, you could have non-causal memoryless systems as well. Those are the pure, like counters. No, not counters. Counters would be a memory system. But you have systems where the data, for instance, they store data, stored information, right? You could play it back, reverse, you could go into it and go forward and so on. And but it may not necessarily be storing the value at a particular point in time. Right, would have been stored already. The other one now is time invariance. Now, time invariant is one of the more important characteristics that we need in order for us to do our work, at least at this level. A system is said to be time invariant if the occurrence of the output changes by some time shift delta t when you change the input by the same time delta t. In other words, if I have something and I put an input now and I get some kind of output, if I come 10 minutes later and I put the same input, I'm supposed to get the same output coming. I'm not supposed to get an output that was adjusted for the fact that it was 10 minutes later, right? In other words, when the output is produced does not depend on time. All right. So in other words, mathematically, if an input x1 gives an output y1, then if I delay x1 by some amount tau, the same output is going to appear delayed by the same time tau. And same thing for the discrete time system. You delay by a certain number of values, the input, then the output is supposed to be the same output, but just delayed by exactly the same number of values. It does not depend on time. So if you look at some of these things, right? For instance, the first one, yt is txt plus 4. So if I change xt to xt plus tau, y is equal to t plus tau plus 4. Is that causal or not? Sorry, time invariant or not? All right. If you look at it, and then you calculate its time invariant, because what happens is that the output at time t minus tau is different than if than at time t. All right, and that is simply because of this bit here. It is adjusted, the behavior of the system is being adjusted for time. It's just not simply a delay and so on. So this particular system is time variant. Then you look at the other one, right? So y nt at discrete time is x squared nt. Again, you could kind of tell that this now, there's not time function multiplying xt at all. So if you were to do the substitution, right, you will find that the output at ynt, the output is x squared nt. If you delay the input by some amount of values m, the output is the same output, but just delayed by the same number of values m. So this particular one is time invariant. And you'll have enough examples in the problem sets to play around with this. The other thing that we might like is to find out if the system is linear. Now, linear is if a particular thing called superposition holds. Now, what is superposition? Superposition just means that if I have a system and I put a signal X onto the system, it gives me some response. If I put input Y onto the system, it gives me some other response. If I put X and Y together, if superposition holds, it means I could just add up the response from X and add up the response from Y and get the answer. All right? So any combination superposition is a system, is linear if superposition holds for any linear combination. And linear means addition, addition, subtraction, or multiplication by constants, right? So AX1, so if X1 gives me some output Y1 and X2 gives me some output Y2, X1 plus X2 is supposed to give me output Y1 plus Y2. And AX1 is supposed to give me AY1, and AX2 is supposed to give me AY2, and so on. All right? Once A and B are scalars. Now that is important for us because if superposition can't hold, in many instances, most of our analysis is impossible to do. So you got to look at these kind of things right here. So YT on the left-hand side, YT is 3xt. If you were to do this substitution and you let some signal be AX1t plus BX2t, if you substitute it inside of there, you see that the output becomes AY1 plus BY2. So that one on the left-hand side is linear. The one on the right-hand side, though, once you make this substitution, you will see that if you put the input and change the input from X1 to AX1 plus BX2, when you run that through now, you get an extra value that is coming in inside of it. The value or the output is just supposed to be the value of AX1 plus BX2 squared if it was linear. But you have some extra factors coming in, which is not the same as if you were to run AX1 in and run AY1 and just add up the two, right? And you could tell that, you know that, just by looking at this index here. An x squared function is going to do that. A linear function does these kind of things. That's linear. Nonlinear functions behave like that. So anytime you have a power, anytime of power appearing, chances are the system is not linear. What we do in engineering is that if you meet a system, and you're going to see quite a bit of that in your controls at some point in time. If you meet a system whose behavior is looking like that, what you do is that you look at a part of the system where you can approximate the behavior to a straight line. In other words, you take the nonlinear system and you choose a set of ranges where it appears to operate linear. Right? Nonlinear analysis is postgraduate design and postgraduate analysis, and there are ways to do that because a lot of big systems in the world are nonlinear. But for your purposes and for undergraduate work and for our signals and systems, most of the times we're going to be dealing with linear systems. And if we can't, we're going to find a way of dealing with a part of the linear system that is at least behaving in a linear fashion. Yeah. So here are some other analyses here. So this is a resistive network, which would imply that it's also memoryless. It could be causal, some of the terms that we used before. To check if it's linear, we have to see if superposition holds. So the output yt is r over r1 plus r2 by xt. So I replace xt by a sum of two signals. So the output should be a sum of the inputs for each of them. I do the substitution in here, and then when I check it out, I find that the output is a sum of the scaled input for x1, right? So a x1, b x2, and of course it's scaled by a scalar factor. This will be a scalar factor. So this particular system is linear. And that is the approach that we would take trying to determine linearity or non-linearity. All right. When you look at this now, you have now, when we take the same RC network and we apply and we introduce a diode into it. So let's say we put an input which is a unit step. So the input coming in here is a unit step. Put yt. So the system, notice if x is greater than or equal to 0, well, assuming a perfect diode, if xt is greater than 0, then the output, the diode will conduct, and this is the output here, right? Y, of course, we take in, it looks like Y, we take in the output across R1 here, right? If xt is ut, then so far we have xt, we have this output here, okay? Not bad. But let's flip it around. If xt is minus ut, in other words, I'm switching it off now, then the circuit does not conduct if we put in a minus ut here. So instead of doing this, I do this, a minus ut. So it's going north to minus 1. If I do that, then because of the diode, the system doesn't give you a result. What it should have done, if we had removed the diode, you would have just simply got minus. It would have given you the same answer, irrespective of the sign. But as it is right now, the system is telling you, plain and straight, the diode ain't going to conduct. So what you're going to have now is nothing. So clearly, a signal on one, you put axt going in, you get some response. You put minus axt, the answer was supposed to give you minus yt coming out, but instead you're getting 0. So this kind of system, once you put in semiconductors into the system, semiconductors give you nonlinear systems. All right, and as we're saying here, many systems are going to be nonlinear. Once you have semiconductors, so that basically means all of the circuits that we deal with, diodes, transistors, FETs, and the like, all of them are nonlinear, right? And then if you get into mechanical engineering, the aircraft dynamics, fluid dynamics, economics, and the like, all of them are nonlinear. For our purposes here, we're going to focus exclusively on linear systems. Why? Because first off, they represent the behavior of many parts, even if the circuit systems or the fluid systems or whatever it is are nonlinear, many parts of them are in fact linear. So we could model that. You could take part of the nonlinear operation, as I mentioned before, and you could, by making it linear or assuming that it behaves linearly over a short period of time, you could therefore go ahead and do the kind of analysis that we want to do. And of course, you have to say in your in your conclusion that right, the system is nonlinear, but for this particular zone, we're treating it as operating in a linear way. And then linear systems are analytically tractable. Fancy word to mean you could solve it. Right? Analytically tractable means that we can solve it. And if we can solve it, then we have some way. Remember what I mentioned before, that we're doing models. So if I give you a very complicated system that is nonlinear, how you're going to model that is going to be very difficult. So what you do is that you look at the system and say, okay, it's nonlinear, but maybe over a voltage range of 10 to 15 volts is linear. Let me see if I can model that part, and let me see what insight I can get into it. So if I understand for this little range of values that this system, it is nonlinear, but for a little range of values, I assume that it can behave in a linear way, and I do some analysis on it, I can get a lot of useful insight into what the real system may do. And then using some of the things that I mentioned before, you make educated guesses. You make some assumptions, and then from there, you can move forward. In fact, and that's how it's done. And what they do normally in the more advanced courses is that after you deal with it in a linear way, you then use statistics and probability to say, okay, if it behaves, so what is the chances are that the real nonlinear system is going to behave in a particular way? And there are lots of analysis that you will do, and you pick up that, especially if those of you are going into the controls stream, when you do advanced control system or control system design, you're going to meet a lot of techniques to deal with nonlinear systems, which do comprise a fairly significant part of the kind of things that engineers have to deal with. All right? That requires a little bit of maths, but engineers, you can't get away from the maths. When you go outside, depending on the kind of field that you end up working in, you may never do a Laplace transform or a Fourier transform again. But again, depending on if you get into certain types of fields, let's say you get into the aerospace industry or you get into the biomedical industry, you're going to have to understand some of the nitty-gritty mathematics in order to design systems that work with those the reality of how those real world systems work. Yeah. So don't run from the maths. It's there. It's our language. Be comfortable with it. If even you're not going to use it, if even there's a good chance that in some cases you may never meet it again. You can never tell where your career will take you. So bear that in mind. Yeah. And of course, bounded systems. Bounded systems simply mean that the amplitude remains finite. So power systems are you're working, you have something that is operating on a 24-volt supply. It means that the amplitude of the output should never, in theory, it can't go past 24 volts. In a physical system, some physical systems should only produce bounded outputs. So like you've seen the pictures where on assembly lines, for instance, they use robots. Robots are heavy industrial devices. The arms and the mechanisms are big chunks of metal, and they're moving around. So clearly, when it has to move from point A to point B, the robot system should have a range of limits to prevent it from moving beyond a particular zone. All right, so all those things, physical systems should always produce bounded outputs, right? If not, components fail, things explode. Right, control systems, for instance, that we have in our environment deal with extremely high temperatures and pressures, but within limits. The piping and the motor and the valves and the containers and so on are designed with limits in mind. If they are not bounded, then an input will come in that will produce something that is beyond the tolerance of a pipe or a container, and it explodes and people get hurt. So a terminology that we use is that systems should have bounded input, bounded output stability. In other words, every type of input that you put on it should produce an output that is within some boundary. right? So nothing that you should do on a well-designed system should produce something that will cause it to go out of control, right? Electric vehicles, you mash the accelerator, you remove your foot from the accelerator, the vehicle is supposed to decelerate, come to a stop. It's not supposed to continue at speed or accelerate beyond the range, right? That's the kind of thing. And a good indicator for a bounded system is that if you look at the response, is that there are no asymptotes. In other words, that it doesn't. An asymptote is like an infinite, is something that after a long period of time it settles to. So from the time you see, you get where am I? You get a response that is looking like that, and it's going up and up. It eventually will assume some value, but after a long period of time, typically an infinite period of time, that is a good system that is not bounded output. All right. So you're looking for that kind of response if you have a graphical output. But basically, our goal is to have this for our purposes. Makes it safer. You don't want things blowing up in the lab. Right? And our course focuses on that. Bounded input, bounded output, linear, because superposition will apply. This, so explosions, this, so we can apply superposition. This, because if you do something today and you come back next week and do the same thing, you're supposed to get the same answer, not a different answer. So it's predictable. The next thing is that if these things collectively called LTI, linear time invariant systems, if you have a linear time invariant system and you see what the step response looks like, you see what the impulse response looks like, and you see what the sinusoidal response looks like, this is the part that we deal with when we do the Fourier response. Then once you satisfy this and you could see what it does for this, then it is possible to predict what the system is going to do for a whole range of other inputs and values, right? And on all of the other types of scenarios that is likely to encounter, up to and including things like discontinuities that we mentioned before, right? That's where the impulse response part will come in, right? So the impulse response, how it responds to discontinuities, a good idea is when you check the impulse response to see what the system actually does. Yeah? So again, it's more descriptive stuff, but just to put what we're doing or what we're planning to do in context. So questions? Nothing?
So you could go over the bounded system one with the when I was explaining the one with the bricks.
Okay, so for instance, right, the example there was that a system, a physical system should produce bounded outputs. In other words, the range of outputs should be confined to some limit. So you have an electric vehicle. The electric vehicle has a minimum speed, of course, 0, and a maximum speed of, let's say, 200 kilometers per hour. Okay, so you're moving around the place, and you are moving at 100 kilometers an hour, and you remove your foot from the accelerator. The system is supposed to come back down to 0. Right? First off, it's not supposed to accelerate. That's the first thing. Secondly, if it does accelerate, it's not supposed to go beyond 200 kilometers an hour. So it has a range of values. Right? For certain movements of the accelerator, it is bounded by 0 to 200 kilometers an hour. Right? It was just to give you an example of something. Or like the steering. You turn the steering to the left and the right. The wheel is supposed to go, let's say, 30 degrees off perpendicular left and right. If you turn it, and for some reason instead of 30 degrees now, you're able to get it to go past 35 and 40 degrees, then clearly you have something that is not, you have no idea what the limits are. So at that point in time, you're dealing with it. You can't predict what a system is going to do. You don't want that. Yeah. So those kind of
Yeah.
things. Just you think about it, and the bigger in terms of mechanisms in the system that you're dealing with. So a vehicle is an extremely heavy thing. Cranes, robots, those types of devices, industrial pressures on flows, on temperatures and the like. Those are high value inputs and conditions. And what you absolutely do not want is that the system ever goes out of those ranges. All right, so there are boilers that operate at, the boiling material, and they're operating at 3,000 psi, pounds per square inch. So what happens if something happens, the fuel line sticks, and the boiler is heating up continually all the time, or it's an electric unit, and something happens and the thermostat fails and it keeps getting current, it keeps increasing the pressure beyond 3,000. What's going to happen? It's going to fail. It's going to fail and people are going to get hurt. So that's why it's all absolutely imperative that when you're dealing with systems that you have bounded systems to deal with. Some things are intentionally unbounded. For instance, weapons, right? Explosive devices, those are unbounded and they're designed with that in mind. And they're designed to be unbounded in a very specific way. But we're not dealing with that. We're not designing those kind of things. We are dealing with bounded electrical engineering systems for the most part. Yeah?
Understood, understood. Thanks.
All right. So any other questions? All right. So at this point in time, so I can stop the recording here.